Hello, everyone. Welcome to our talk on running machine learning challenges with Kubeflow. Great that you are here. My name is Hannes. I work as a computing engineer at CERN.
And my name is Raul, and I also work as a computing engineer at CERN.
So let's start with a very quick introduction of what we do at CERN, what's our goal, what our objectives are. So CERN operates the world's largest particle accelerator, which is called the LHC, which stands for Large Hadron Collider. As you can see on this small animation, it took me way longer than I wanted to make it. We accelerate proton beams to nearly the speed of light. And as you can see, it's an accelerator which is built underground, around 100 meters, under the French and Swiss border, under the city of Geneva. And why are we doing this? We want to deepen our understanding about fundamental physics. We want to know more about the building blocks of nature and of the universe, which consists of different kinds of particles and all the forces that act between them. So how do we do this? After we accelerate the particles in our big loop, which is like around 30 kilometers circumference, we let them collide at our experiment sites. And what we do here is we use the high energy of the particles that they got during acceleration and transform the energy into mass by creating new kinds of particles. And those can range from particles that you maybe know from school, protons, neutrons, electrons, but also to more exotic particles like pions, kaons, and neutrinos. This process acts at 40 million times per second, so the whole machine operates at 40 megahertz. And if you want to read out all the data that's available to us, we will end up with around 40 to 50 terabytes per second, which is too much to be handled by our current capacities. So for that reason, we employ a filtering process, which is a so-called trigger system, which consists of two levels. First, the level 1 trigger, which is a hardware-based filter selection process, where we just use simple rules to discard events that are not very interesting to us. So for example, if we have a collision event with a very high energy, that's something that we want to keep, and that's something that we want to store. Events with a low energy is not interesting to us. There's no new physics, so we will discard it. After this first step, we step into the level 2 trigger system, which is a software-based approach, which runs in computing farms very close to the actual collision point. After this part, we end up with around a few gigabytes per second. That's something that we can handle, and that's something where the end data will go into long-term storage. And now, recently, we started a research and development project, which is called the Next Generation Triggers, where we want to employ machine learning-based methods on improving the whole chain. So the goal will be to use machine learning models in the first step, in the level 1 trigger, but also in the second step, in the second level. What do the physicists do at CERN working on these trigger systems? So we have different use cases for machine learning. The first one is the reconstruction of particle positions. As I showed you in the beginning on the animation, all these particles that get created, they will interact with the big machine, and you can detect each position during the flight of the particle through the system. And the goal here is to identify which points of interaction belong to one track. After you have done this, you also want to classify the actual particle. Because in the end, you have the interactions, but you don't really know what kind of particle it is. So it could be an electron, it could be a proton, but it could be also a neutron. That's why we use classification to, in the end, identify the actual type. As I mentioned in the beginning, we are mainly interested in new physics. So we actually want to look for anomalies in the data that we process. So in machine learning terms, we do anomaly detection for the discovery of new physics. And something that we want to provide to our users, to our physicists inside this community, is a new platform, a new service, where physicists can participate in machine learning competition challenges, like the Kaggle system, if someone knows it. And all the physicists can participate in, let's say, call it a game. It's like a gamification process, and everyone competes on a place on a leaderboard. And for more details, I will hand over to my colleague Raul.
Hello, thank you, Hannes. So to start with the question, who here has heard of Kaggle? OK. Who here has used Kaggle? OK. So basically, this diagram up there might look quite familiar to you. It is a Kaggle simple challenge. Basically, you write your training code and your inference code, and you run it on your own hardware, and you get a prediction file. And then you submit that on Kaggle to calculate your score. So why is this pretty good for machine learning? Well, it's a good central entry point for the research community. It promotes collaboration across teams, tasks, and data sets, and it reduces the barrier to entry for people to participate in research. You can just go on Kaggle and do the usual Titanic challenge, and you can learn more about machine learning that way. But what we want to do at CERN, we want to do it ourselves. Why do we want to do it ourselves? Well, for data protection, not every CERN dataset is open, and we want to have full control of maybe possible sensitive datasets and code. We have good fine-grained access control. We integrate with our internal tooling that people need to use or want to use, and we control the resources behind it. So we would have a shared pool of on-premise resources. These resources are optimized for multi-node and multi-GPU configurations. And this way, we can give a fair boundary conditions for all participants. So our setup would look kind of like this. This is on Kaggle. This exists also as a code challenge, where the user only submits their code, and everything is executed on the Kaggle platform. And this is, and this way, the person with the best resource, best on-premise resources doesn't necessarily win, but the best code wins. And this is what we want to achieve. So the user would just write the code for training and inference. We would handle data transparently, and the user would just submit their code as a container image, and it would look something like this. Just reading the data set, creating their model, their inference code, and send it. So what do we need to achieve this? Well, we need the user interface to manage these challenges and submissions. And we need an MLOps platform for scheduling and running user submissions. Well, can you guys guess what MLOps platform this is? Well, at CERN, as a bit of background, we've been using Kubeflow in production for quite a while, and it is the main entry point for running ML workloads. We use the full Kubeflow stack with notebooks, distributed training, HPO with Katib, serving with Kserve, and of course, Kubeflow pipelines. And it's fully integrated with all the CERN storage backends, database services, our own OIDC, and networking services. Our infrastructure for the ML platform based on Kubeflow is quite heterogeneous. We have a bunch of high number of CPU core nodes. We have a few T4s that are good for notebooks, V100s, A100s, H100s, and soon to be AMD GPUs, as well as maybe some ARM devices as well. In terms of profiles and quotas, we provide users with personal profiles. This is the profile when you initially go on our platform. It gets automatically created for you. You get a quota for 1 GPU and 30 GB of block storage based on CFFS. And for team profiles, in case a user wants to run I don't know, something beefier, let's say they request it and they get higher quota on demand for this. So in terms of how we deploy Kubeflow at CERN, everything is based, we do with GitOps, with Argo. Of course, we use Customize, and we manage secrets via Vault. For some integrations with storage systems at CERN, we need to authenticate with OIDC. We mount this storage system as a home directory for users in notebooks. So we need to propagate these authentication tokens somehow to the notebooks. And we wrote a custom controller to inject these tokens and refresh them. And we also use Kyverno for overriding the home directories in notebooks. And we set some restart policies on sidecars that are not yet supported by pod defaults, but we hope to contribute upstream for this to be supported. So I'm going to pass over to Hannes for getting a bit deeper into what the workflow will look like for the Challenges platform.
Yeah, thanks, Raulian. So yeah, Kubeflow pipelines is the ideal tool for our goal. So we use Kubeflow pipelines for the orchestration of the submissions of participants. A rough overview of how the system looks like. So everything is based on top of Kubeflow. We have challenge maintainers, so they are responsible for creating a challenge. They have to write down how the data looks like, where the data is stored. And we also have the challenge participants, so these are our actual users that want to submit their solutions. For this, we use a separate UI, which in the end will start and control pipelines, running the training of the user, the inference, and also the scoring. From within the pipeline, the user can access KTIP for hyperparameter tuning, but also the training jobs for distributed training. If we look now through the different steps, so we will go through all of them in detail in the next slides. So the first step can be the download and the preparation of your data set, which will create the input data for the user code, but also the truth data set, the ground labels later for evaluation. The next step is the execution of the actual user code. So the user writes this training code and also the inference on the test input data. After that, we get the prediction output. And on that, we want to calculate a score. And afterwards, submit the score to the leaderboard so that we can have some feedback for the users and also for the challenge itself. OK, the first step, the preparation of the data set. This is very useful if you want to download the data that's externally available. And it's something that the challenge maintainer has to provide, ideally as a Docker image. And the challenge maintainer also has to write down some details about the data so that the users know how to interact with that. So how do the files look like, what's the content, all of this has to be filled in during the challenge creation. And this approach is very nice if you want to integrate small data sources from external sources. Okay, the second step, running the actual user code. So this is something that the participant would provide to us as either a Docker image or as a Jupyter notebook. From within the code, as I said already, you can interface with Kubeflow during the SDK. And the input to the user code will be the trained data, so the input and the labels, and also the evaluation data, but of course only the inputs. This would be passed as a KFP dataset from the step before, or it can be also the path to a directory in a mounted volume. The output of that, okay, of course, is the prediction based on the test input data, and it would be outputted as a KFP dataset again for further processing. Now, calculating the scores on a test dataset. So this component is again provided by the challenge maintainer because it highly depends on each challenge, on each use case. So this could, for example, be like an accuracy metric for classification. And in this case, the prediction from the user code and the scoring itself, like the score value, are passed again as a KFP dataset. The evaluation data, the ground truth data that is needed to compare to the user prediction, is passed as a KFB dataset, or again via a path to a directory in a mounted volume. Now in the last step, the submission of the score to the leaderboard. So what we get here is we get the evaluation score or the scores from the previous step, passed as a KFB dataset, and we submit it to our custom backend for the challenges. And we can use these scores in the end to visualize to the participants, but also to give more feedback. This component is provided by the platform itself as either a container component or as a standard Python component. Okay, how does the user interface look like? So this is the entry point for the challenge maintainers, but also for the participants. So for this, we developed like a small frontend and a small backend, which is deployed in a separate namespace in our Kubeflow cluster. For the frontend, we use Angular. It's integrated as a Kubeflow dashboard app. As you can see, there's like a small new tab spawning in the sidebar. And for the backend, we use a Python Fast API framework, and of course the KFP SDK to control the pipelines. Okay, looking at a small demo. So now we have our testing instance of our Kubeflow cluster together with our integrated challenge user interface. So the first thing we want to do is we want to create a new challenge. Let's put in a name. So we want, in this case, we want to download some external data. And we have to pass the path to an image. The same goes for the scoring image. So this is the component which will actually calculate the score. And we can also give some basic description about the challenge and also about the data. So let's pass that in. So this is passed as a markdown file. And let's submit. Okay. So now we have a list of our challenges. If we look at it, okay, we can see I created my challenge. In this case, for the demonstration, it's the iris classification problem that maybe many of you know. It's about classifying flowers based on some simple features like the sepal length and width. If we go to the data tab, we can see all the information that is needed to understand how the data looks like, what are the features for the trained data set, what is the input data on the test data set that we have as a user, as a participant that we have to train on. And also, we can see our leaderboard, which at the moment is empty. Okay, let's submit a solution. We give it a name. We pass the path to our image. And we also pass the command to actually execute the submission code inside the container. Okay, so now we submitted it. And if we now go to the tab for the runs, we can see that a new run spawned. These two are some previous tests that I did. So if we now look into it, we can see the graph that I showed you before earlier. So let's wait a little bit until it runs through. And let's have an example look at how the code looks like. So first, for the downloader component, this is again something that the challenge maintainer, like the creator, has to provide. We pass in the output path for the training data and the test data for the user code. So in this case, we pass it as a command line argument. And the same, the output path to the ground truth data that we will eventually lose for the evaluation and the scoring. Then we prepare our data set. We write our train data frame, save it to the path that we got from Kubeflow pipelines, and do the same for the ground truth data set, where we only have the ID of our entry row and the species. Okay, if we look at our pipeline, we can already see that it started the containers and went through. So we can see the download step is already finished. It created 2 output artifacts. and it was already running the user workload, so it was quite fast. Let's check out that one. So again, this is the submission part. So myself as a participant in a challenge would write the code. I would get the input path to the training data, and also the output path where I have to put my prediction file. Okay, so in this case, I read in the trained data CSV. I get my usual features. I train a very simple random forest classifier. Then I read in the test data set. I pass in the features. I run my prediction. I create my prediction data frame, which consists of like the entry row ID and the predicted class. And then I write down the CSV file to the specified output path. Okay, let's have a look. So this went through. We can see our output for the prediction. The next step is the evaluation. So again, this is the part that the challenge creator maintainer would create. And in this case, we get the input path to the prediction file where we have the prediction from the user. We also get the output path to the scoring file. So this is in the end where we will write down the scoring, in this case accuracy. It will also get the path, the input path to our ground truth labels. So in the next step, we read in the data from the user. We have the predictions. We also read in the ground truth labels. And then we just calculate the accuracy and see how well our user did in this case. And then we write down the score. And in this case, it's only one score. It's the accuracy on a prediction. And we can see it went through and created an output artifact for the scoring. Then in the last step, we report the score to the challenge backend. And if we now go back to our user interface and we go onto the challenge, we should hopefully see a scoring for my user account. Okay, how would we handle data? There are a few questions that we have to ask ourselves. How do we want to handle the training and the evaluation data? Are they loaded from external sources or are they already available internally? Do they need to be accessible from training jobs and from K-tip jobs? And also, how do we want to pass data between all these pipeline components, between the steps? Because, for example, the prediction output from the user component can potentially be large. Also, do you want to have the prediction accessible from the pipeline dashboard? And for this, we have several options. So we can either use the S3 artifact storage, the default by Kubeflow pipelines, or we can use a persistent volume. And here we have, again, two different options. Once, do we want to have a persistent volume for each run, for each submission run, or do we want to have it available across the runs? Should it be available for the whole challenge or across challenges? And for the data passing inside the pipeline itself, we have to decide, okay, do we want to pass only the reference to the location on the PV, or do we want to use the KFP placeholders for the input paths and the output paths, which in turn would require changing the actual data passing methods. Okay, and we are over time, so we have to finish quickly. There are three options. So you can either pass small external data. You can also use large external data. Or we want to use an internal data set that is internally available via persistent volume. A next step, how users can submit their solutions is via notebooks. So notebooks are very useful for iterative development, where participants are able to play around before they actually submit to the full resource usage. And similar to before, the challenge data is mounted transparently. And eventually, we also want to implement a feature where the submission of the notebook goes for full execution. So I will skip the demo for this for now, and will hand over to Raul for the roadmap.
Yeah, so we are in a bit of early stages with this project, so the roadmap is quite long. So we want to integrate with other Kubeflow components like Katib and training jobs. In terms of eligibility, we can have open challenges with open data maybe, or challenges within a CERN collaboration where data access will be more restricted. And we will need to do an authorization process between challenges and OIDC groups. In terms of different types of challenges, this could be resource constraint, time constraint, maybe only run on CPUs, maybe only run on ARM devices or GPUs. In terms of quota management, how do we handle this? Do we do it per challenge? Do we have a shared pool for all challenges? We need to give the challenge maintainer more flexibility in defining their user scores. We need to also rate limit user submissions, so we just don't take up all the resources available. And we also need to expose the results of these challenges in terms of the models via model registry and the code, advertising the either image or directly the code of the winners. And maybe even maintaining an open source component for this. In terms of the roadmap for the machine learning service at CERN, we need to work more on automated management of team profiles. I know there's a lightning talk a bit after this, so maybe that will have something to say about it. We need to improve GPU availability and resource sharing. For example, by adding MPS to our MIG setups that we currently have. We've been looking into DRA as well and are working closely with NVIDIA and upstream Kubernetes for this. We also want to integrate with Q and especially multi-Q for bursting to the public cloud if possible. And finally, dedicated team serving entry points. So maybe some of the models of some of our users at CERN that are served will have a lot of traffic, and we somehow want to figure out a way to have different load balancers per team profile, for example, that we can get traffic into. And that was it. Thank you.
We have time for questions.
Hello. Yes, it always makes me happy to see the whole Kubeflow platform used. But I have a question. You mentioned OIDC several times, and you have to do some manuals. Yeah? Can you hear me now?
Yeah, now I can.
OK. I saw on a few slides that you use OIDC to some degree manually. And I'm wondering on which version you are, because I think 1.9 and 1.10, they have full support to use the default editor service account to authenticate to the whole Kubeflow API, for example.
So we are currently on 191, but we've had difficulty migrating to OAuth 2 proxy currently due to a bunch of details that I won't get into now. We can discuss afterwards if you want.
Yeah, that's fine. Let's do it afterwards.
Yeah. Any other questions? We have 1 minute for question. All right, thanks for the great talk.